the first of the lecture series that really gets into seismic stratigraphy, which is my strong suit. So I always enjoy giving this lecture on seismic sequences. This is my obligatory terms of use slide, and I'm not going to read everything. Basically, the materials, the videos, the exercises, the lecture PowerPoints are intended only for student training, and that would be done at universities or colleges. It is not intended to be used for people who are already employed, especially within the oil and gas industry, and is not to be used by other instructors in a for-profit setting. Okay, so let me talk first about the importance of stratigraphic information. Of course, sedimentary rocks are critical when we're looking for oil and gas. One of the things we need to worry about is where source rocks are, and those typically are organic rich shales. We want to know where our potential reservoir rocks are. Those could be sandstones or coarser clastic rocks, or they could be coarse-grained carbonates that have porosity and permeability. We also are interested in rock formations that will form seals. These seal units are usually fine-grained shales or any type of an evaporite. And we're also interested in trying to understand lateral hydrocarbon migration pathways. And so all of this leads us to a need to try to understand the sedimentary fill within our area of interest. So the goals of seismic stratigraphy, given seismic data, what we are trying to predict is the location of rocks that will serve as sources, reservoirs, seals, and migration pathways. We're also interested in rock properties that are associated with these stratigraphic units. And so our procedure is first to break out major depositional sequences, and that's what we'll focus in on today. And then in a future lecture, I'll talk about how we predict environments of deposition, alluvial, fluvial, nearshore, continental shelf, slope, basin. From the environments, we'll infer lithologies or rock types. And the other thing we would like to do is model how rock properties have changed from what they were initially at the time of deposition to what they are present day at their current burial depths. So I think last week I talked about the depositional sequence. I'm sorry, I talked about that on Tuesday. This is Thursday. A depositional sequence is a relatively conformable succession of genetically related strata, bounded at its top and base by unconformities or their correlative conformities. And this definition comes from Vail and others, 1977, Mitchum, 1977, Van Wagner, 1991. Whenever I have a reference to 1977, that is AAPG Memoir 26, which is the foundational book for seismic stratigraphy. And this is a classic figure from Memoir 26, and I'm going to go through this figure on the next slide. So we'll look at that definition, we'll tear it apart, look at it piece by piece. The first part, it's a relatively conformable succession of genetically related strata. So that means we have a package of sedimentary rocks that are representative of a geological period of time. Depositional sequences are usually associated with geological periods of time on the order of 3 to 10 or 12 million years. They are bounded at its base by an unconformity. And so I've labeled a few of the layers here, A, B, C, D, E. And you can see the extent of layer A and B steps out from that, and C and D and E all step out from that. The bed boundary or the parasequence boundary between A and B comes down and gets so thin in this position that we no longer can see it seismically. Similarly, the boundary between B and C, C and D and E. We call this type of relationship downlap, and I'll give a more formal definition in a few minutes. But you can imagine if we drilled a well, let's say where this E letter is, and we got down to the line with the cyan dotted blue, we would not see any of unit A or B and just a little bit of C. So there is a break in deposition, and we know that by the fact that these units are downlapping. We also have some evidence of the top of A onlaps out and the top of C onlaps out. So again, another indication that we have a break in deposition or an unconformity. And where we don't see any discordance, non-parallel layers above and below the boundary, that's what this correlative conformity is. So I have evidence for a break in deposition or an unconformity on the left. I have another one on the right, and the two segments in the kind of gold color are where I don't see any evidence for the break of deposition. So that's what we mean when we say correlative conformities. It's also bounded at its top by an unconformity. So I have layer X, Y, and Z. So if I drilled right where that little green arrowhead is, I would not see any of unit Z. Similarly back here, if I drilled where this arrow is, I would see unit E and most of F, but I wouldn't see any of the younger units. So I have two places where the geometries of the strata are telling me I have a major break in deposition or an unconformity, and then the rest of that surface where I don't have evidence based on the geometry of the strata for a break in deposition, that would be the correlative conformity. So seismic sequence, I've been talking about a depositional sequence. A seismic sequence is simply a depositional sequence that we identify using seismic data. And I'll talk more about this as we proceed, but what we look for is the termination of reflection cycles. This is an old piece of 2D seismic. The blacks would be the peaks, the whites are the troughs. And so I put red lines with arrowheads to mark where some of these peaks or black half cycles terminate. And those are indications that I have a break in deposition. So I have a yellow sequence boundary, I have a green sequence boundary, I have a blue sequence boundary, an orange, and a purple. So how do we recognize depositional sequences or seismic sequences? Well, by definition, they're bounded at least in part by unconformities. So what we'll do is we'll look for evidence for unconformities so that we can identify these surfaces that separate one older depositional sequence from a younger one. So let's go to Arizona. This is a view of the Grand Canyon. The photograph is being taken from the south wall looking at the north wall. And you can see banding in there related to major depositional packages. And if I add some lines, towards the top of the cliff, things seem to be fairly parallel. Towards the base of the cliff down by the river, which is not quite visible in the photograph, the banding of the stratigraphic units is dipping down to the right. And so I can break this into two mega periods of deposition. The first is characterized by the units that are dipping down to the right, or that would be towards the east. Then I have a major break in deposition. Some of it is buried by the talus slopes, but it's about where the magenta line is. And then I have a second later phase of deposition, which is characterized by nearly horizontal layering. It turns out that the earlier mega phase of deposition is Precambrian in age, And the second major phase of deposition is Paleozoic in age. I also know that the height of the North Wall is at about 8,000 feet. These are shallow water sediments, and so there must have been something after the Paleozoic period that caused these rocks to go from close to sea level up to 8,000 feet, and that's the Colorado Plateau uplift. So by looking at the major stratal units, trying to figure out where I have breaks in deposition, I can identify places where I have unconformities. If I look at seismic data, and if I believe Vail and Mitchum when they say seismic reflections tend to parallel stratal packages, then I can start looking at the reds, which would be a trough or a white on a black and white section. I can look at the blues, which would be the blacks or the peaks on a black and white section, and I can start to mark them. So this red comes up and looks like it terminates. This red comes up and terminates. This red comes up. This red comes up. This red comes up. And above that, if I again mark just the reds, I see different terminations. And so I can draw in a boundary, and we would call this a seismic sequence boundary, separating an older period of deposition from a younger period of deposition. And so I have older rocks, a break in deposition at a significant unconformity, and a second phase of deposition sitting on top of that. So it's through the termination of seismic reflections, peaks or troughs or both, that I am able to get some evidence for these breaks in deposition or these unconformities. So Vail and Mitchum codified this for us in Memoir 26. They talk about Onlap terminations. And so in the darker orange, these would be older units. And so I'm looking at what's deposited on top of those older beds. And I have either stratal packages that I could see in Outcrop, or I have peaks and troughs that I would see on seismic. And this, let's call these reflections. Maybe this is a peak, it terminates. The next peak on my seismic terminates, the next one terminates. If the terminations are on reflectors that are at a gentler angle than the surface against which they terminate, we call that Onlap termination. Alternatively, or similarly, again, the orange would be the older rocks. I have a seismic reflection that comes and terminates, another reflection cycle that terminates, another reflection cycle that terminates. In this case, the reflections that terminate are at a steeper angle than the surface against which they terminate, and this is what we define to be downlap. So with both onlap and downlap, it is purely the geometry of the stratal units that we use to make the definition. There is nothing about sedimentary type or rock type or environments of deposition or sea level that's associated with onlap terminations or downlap terminations. There are simply pieces of evidence that Sherlock Holmes looks at and says, elementary, my dear Watson, there must be an unconformity here. Sorry about that. So we map or mark, and the traditional color for marking the sequence boundaries in an initial interpretation is to use yellow. So again, seismic sequence boundary is marked underneath the downlap arrows and underneath the onlap arrows. At the top of the sequence, we can see two types of terminations. Perhaps we had some post-depositional erosion, and we've cut away some of the older unit, and we'll infill that with a younger sedimentary package, and we call this erosional termination, or simply erosion. And this is a geometric relationship, but it also has a little bit of geology thrown in there because I'm calling upon erosion as the reason for the termination of the reflectors or the break in deposition. The other thing I can have is if I have a big deltaic package, I can have units that build out basinward. And so the reflectors come up at a moderate angle and then they start to roll over and almost asymptotically approach a constant level. And if I have this type of geometry, I call that Toplap. The reason why these units get thin and the reflectors terminate is because as I get into shallower water depth on the delta, the units are not thick enough for seismic to be able to resolve them. And so I'll see a series of Toplap terminations marking a significant break in deposition or a seismic sequence boundary or an unconformity. So again, the seismic sequence boundary, we look for the erosional truncation terminations. Again, I use a red pencil and mark lines with little arrowheads, or we look for Toplap terminations and put the boundary just above those reflection terminations. So erosion and Toplap are largely geometric, but it does have a tad of geology thrown in. Erosion is a post-depositional process that causes the break in deposition. Toplap is more of a syn-depositional reason for the termination of the reflections. We can look at some outcrops and we can use the same type of terminology. This is an outcrop in West Texas. It's in the vicinity of El Capitan. Some of the older units, I've marked a couple of the major bedding surfaces and put some arrows where those surfaces terminate. And then I have some younger units. They're thick here and they thin by Onlap. And so I can put in a boundary there. And it turns out that that boundary actually, in this case, separates carbonates, shallow platform carbonates, from clastics, sands and silts and shales that are river deposits that were infilled when a incised valley or a gully or a canyon was cut into the carbonate bank and subsequently infilled by sands, silts, and shales. So on this outcrop, I have 1, 2, 3 examples of Onlap termination, and I have 1, 2 example of erosional termination. And here's a seismic example. This is from the Gulf of Mexico. Rick Boboff and his co-authors published this in 2003. I believe there's a little bit of a mask on the far left, so the amplitudes are artificially dimmed a little bit, but you can see a surface marked in yellow here at a fairly significant dip, and on top of that, younger material has been deposited almost horizontally. And so this is a major unconformity, an important but less major unconformity here, and I can use the termination of the reflection cycles. In this case, I've been marking the reds and not the blacks. I could mark both reds and blacks and find evidence for where the sequence boundaries or unconformities are positioned. This is another outcrop, same general area, West Texas, near El Capitan. I'm going to show an example of Downlap. This is the younger unit, carbonate, that carbonate margin that's building out into the basin. So these would be paleocontinental slopes. Below the talus slopes, the units are more horizontal. These would be distal carbonates. And so I've dashed in there the approximate location of the boundary, separating the older units, more horizontal, marked with the red lines, from the younger, inclined at a deeper, steeper dip, carbonates that are marked with blue. And here's a seismic example of Downlap. Again, this is somewhat older data, and so we use our red pencil and we mark lines and put little arrows where we think the black half cycles terminate. And so I have 1, 2, 3, 4, 5 downlap terminations, and then I put the seismic sequence boundary, the yellow line, underneath those downlapping arrows. Example from, this is in Utah of Toplap. So I've marked 2 of the units in blue, some of the older units in red, and this package here is coming up, approaching those blue, and I lose the top of it here, and I lose the base of it here. This unit is thinning and thinning. Similarly, these units are thinning and thinning. In this case, I think this is not due to erosion, but it's due to a delta that's building right to left into a basin, and we may have had a slight fall in sea level, and then as it rises, we got the rocks with the blue lines sitting on top of that. So again, we use the termination of the stratal surfaces marked with the arrowheads to locate where the break in deposition or the unconformity is positioned. And here's a seismic example. Again, a piece of old 2D seismic. I've used the red lines to mark the blacks, the peaks, and put arrowheads where I believe there are terminations. Again, I think this is that classic toplap where it's inclined, it starts to bend over, and then it's clipped, if you will, at a fairly consistent level. And it looks like I have 1 pulse of deltaic deposition, something happened, and then I had a second pulse of deposition. So I have actually 2 seismic sequence boundaries marked on this piece of seismic. So what we can do is we can look for terminations of reflectors, onlap, downlap, erosion, and toplap, and use that as an indication of where to put the seismic sequence boundaries. So I have 1 yellow line, a second yellow line, a third yellow line, and then the package of rocks between 2 successive seismic sequence boundaries would be a seismic sequence. So I have the green sequence, I have the blue sequence, and I have the orange sequence. There is a convention that we used at Exxon, and that was if I have a colored seismic sequence boundary, such as yellow, then the sequence sitting on top of that would be given the same name as the color of the boundary at the base. I said initially we make everything yellow. At some point in time, you're going to figure out which boundaries are regional and important, and then you start to color code them. So I have the yellow boundary, the green boundary, the blue boundary, the orange boundary, the purple boundary. And so if this is the green sequence boundary, the rock sitting on top of that, the depositional system sitting on top of that would be the green sequence. Here's a blue boundary, so this would be the blue sequence, an orange sequence boundary, so this would be the orange sequence. I'll be talking about the depositional model that Exxon colleagues put together and published a number of years ago. And when I get to that discussion, it will become clearer as to why we have this convention of using the color at the base to define the sequence the sequence as opposed to the color at the top. There is a very important exercise associated with Unit 21, identifying seismic sequence boundaries. Line C is from offshore West Africa. It was published in 1977, so hopefully you know by now to associate that with AAPG Memoir 26. Paper copies of this were distributed to a number of universities, so it has been used for almost 40 years as a way to train students. And at the IRIS web pages where the lectures and the exercises are located. There's I think it's a PDF, I can't quite remember the format, of this entire line, and you can print this off, and the exercise is to try to identify a number of sequence boundaries on this classic line C. This is the central portion of line C. So sea level is up here. We have about 150 meters of water depth to 200 meters over here. And I'm going to get you started on doing some interpretation here. First, we can put in a couple of faults. There's a fault there down to the west, another one down to the east, another one down to the west. Now let's start to look at some of the stratigraphy, and what I want to focus in on is the interval right here. I see some pretty dark and white reflectors, so high amplitude, fairly parallel, and very continuous. So let me mark a couple of those. So there's one black or peak. There's another one, and I'll mark that one as well. Then there seems to be something different going on just above that. And what I see are reflectors that are coming down at a steeper angle. And these reflectors are lower amplitude than these guys. They're not quite as blacks and whites. If this was in color seismic display, you'd see that even better. And these are not as continuous as these guys. And so I put some arrowheads on these, the dipping inclined reflectors. And if I was doing this live, I would ask the audience, what kind of terminations are these? And I know everybody in my audience today would yell back downlaps, which is correct. And so I can put a seismic sequence boundary right through there. And so I'm saying I have an older period of deposition, and right here I would characterize those reflectors as high amplitude, fairly horizontal, very continuous, and a younger rock formation where the dip is down to the west. The reflection amplitude is moderate to maybe even low, and the continuity is fairly low. I'm going to move to the right on this seismic line on the next slide. So this is what we were just marking. And so I also see here some higher amplitude and continuous reflectors, but they are inclined at quite a steep dip. And on top of that, I see these lower amplitude, less continuous reflectors coming up and terminating. And so I can continue that seismic sequence boundary through this region. If I was doing this with a live audience or audience in my presence, I'd say, what kind of terminations are these? And everyone would correctly yell out, Onlap. And so I have a section here and further to the left where downlap tells me I have a break in deposition, and a series of onlap reflections over here, and that happens to be the same boundary. So I won't go further into the interpretation of this line. That's a little teaser to show you that with a red pencil and a yellow pencil and a copy of line C, you can go in and do some seismic stratigraphy on this particular line. So that concludes my prepared remarks. I'll turn it back to Dr. Bohin and see if we have any questions from our audience.
All right, thank you for that, Fred. That was really interesting. I can tell that you're very passionate about this particular subject.
Right.
Right. Does anybody have any questions now?
I'm a fan of Sherlock Holmes and Dr. Watson.
It sounds like a lot of fun. What's your favorite part?
What is my favorite part of
doing the seismic sequences? The exploration, kind of the detective work of the whole thing?
Yeah, my favorite thing is to take about 30 minutes using this line C and developing an interpretation from Jurassic up to the Pleistocene. And I claim to the students that are doing the exercises with me that I can get more geology out of this piece of paper with black and white squiggles on it than they ever imagined was possible.
That's the truth.
And so usually I give them like 15 minutes to mark some arrows and some red lines and some yellow lines. And of course, they already have learned how to mark faults. And then I usually gather them around the front board with my marking pencils. And I spend about 35, 45 minutes giving them the history of this area. The seismic here is probably shot in about 1964, and they drilled a well on this line in about 1968. And so we talk about what should they have gone after and what did they actually find. And that's always fun, and the students always seem to enjoy that.
Oh, that sounds cool. All right, we've got some questions coming in. The first one is from Carlos. This question is related also to the last lesson. Is there any relation of play types with a stratigraphic hierarchy in between sequence stratigraphy and clastic and carbonates?
Yes, and we'll talk more about that later on. I'm trying to see on my schedule here. I'm not seeing exactly where. I'll talk about it somewhat in the seismic facies and the seismic attribute lectures that are coming up later this month.
All right. Okay, good. Joa wants to know, can we find oil and gas traps around seismic sequences?
Oh, yes. That's the reason why we do the seismic sequence analysis. We're trying to figure out where we have potential source rocks, where we have potential reservoirs, where we have potential traps, get a feel for how large the trap might be. Is it going to hold an economic amount of oil or gas?
All right. That was a very concise and well-described answer. All right, those are the only questions that we have today. I think you must have just explained it all very brilliantly. Oh, here's one more coming
well, thank you.
from Patrick. And he wants to know, was this line migrated and had diffraction corrected?
No, this line has not been seismically migrated. As I mentioned, I think acquisition was in about 64, processing would have been 64, 65. And back in the dark ages, we only had mainframes with less memory than's on most of your iPhones. And so seismic migration, we knew how to do it, but unless it was a highly structured area, it was too expensive and took too much time to do migration. So line C, let's see if I can get back up here, is fairly old seismic data. It has not been migrated. And if you see the sea floor, it's got this little wavy thing in here. And this has got this little wavy thing in here. This is at what is called a water bottom multiple. And so these data are far inferior to what most modern seismic processing would give us. But in spite of all the limitations, I can still weave a very nice geological story here. And they did drill a well on line C, and I don't really want to give away what they found there in case somebody wants to go through the exercise. And there is an exercise solution that shows the interpretation.
Cool. I'll have to check that out. Any more questions? All right, I think that might be it. So please join us next Tuesday on September the 12th, where Fred will be talking about thickness maps. All right.
And next Thursday, we'll kind of continue the size strat and get into seismic facies and then seismic attributes. and reservoir quality and all sorts of good stuff.
All right, sounds fun. We'll see you all then. Thank you again, Fred. We appreciate your time and expertise so much.
Thank you, Dr. Bohan. I appreciate you moderating.
Absolutely. Talk to everybody soon. Bye-bye.